All right, everyone, welcome back. Get ready, because today we're going deep on tissue engineering and regenerative therapies.
Really exciting stuff.
It is, yeah. We're talking about like growing organs in a lab, repairing damaged hearts.
The stuff of science fiction.
Yeah, exactly. But becoming more and more a reality, which is pretty amazing.
It is.
And we're going to be looking at a chapter from Bailey and Love's textbook.
The surgeon's Bible.
Exactly, to get all that high-yield info.
For sure.
Okay, so I guess let's start with like the big picture. Like, what do these therapies mean for a patient, especially, in surgery?
Okay. Well, imagine you have a patient, right? And they have a really damaged knee joint, like severely damaged.
Okay.
So instead of just like managing their pain, we might actually be able to use tissue engineering to repair the cartilage.
Right.
Or like for burn victims, we could use, lab-grown skin graft to treat them.
That's incredible.
Yeah, and that would like really help them recover better and, improve their quality of life.
That's amazing. So we're talking about like actual regeneration and repair, not just managing symptoms.
Right, exactly.
And Bailey and Love's mentions even more ambitious stuff, right?
Yeah, for sure.
Okay.
They talk about like bladders, intestines. They're even working on creating pancreatic islets for diabetes treatment.
No way. Pancreatic islets. That's amazing.
It is.
And beyond just treating conditions, like I read that this stuff can also help us model diseases and test new drugs.
Oh, absolutely.
So that opens a whole other door for research.
Yeah, for sure. If you think about it, like being able to recreate a specific disease in the lab, I mean, that would allow us to study it way better and test potential therapies more effectively.
That's huge. Okay, so we've got the potential, but how does all this regeneration magic actually work? What's like the foundation of it all?
Cells. Cells are the building blocks.
Of course, yeah.
And when we're talking about regenerative medicine, the real stars of the show are stem cells.
The cells, yeah, stem cells.
They really hold the key to the whole process.
Remind me, what makes stem cells so special?
Okay, so two key things, right?
Right.
First, they can self-renew. So they can divide and make copies of themselves like forever.
So they're like unlimited.
Pretty much, yeah. And that's crucial, when we need lots of cells for these therapies.
Makes sense.
And second, they have potency.
Potency.
Yeah, so they can differentiate into all sorts of specialized cell types. Like they can become muscle cells, nerve cells, heart cells, you name it.
Oh, okay. Yeah, I remember that now. But there are different types of stem cells, right?
Yeah, so we have somatic stem cells.
So
Those are found in specific tissues like bone marrow or muscle.
okay.
And they have a limited potency. Like they can only become certain types of cells, within their tissue.
So they're more specialized already.
Right, exactly.
Gotcha.
Then we have embryonic stem cells.
Embryonic.
Which, as the name suggests, come from embryos.
Okay.
Those have the highest level of potency. They could become any cell in the body.
Wow. But I imagine there are ethical concerns with those.
You are absolutely right. It's a complex issue.
Yeah.
But then we have induced pluripotent stem cells, or iPSCs.
Ah, iPSCs. I've heard of those, yeah.
And these are, they're a game changer.
How so?
So basically, scientists have figured out how to, reprogram adult cells.
Reprogram.
Yeah, like skin cells, for example. They introduce specific genes, and those genes basically turn back the developmental clock of the cell.
Wow.
Yeah, so the reprogrammed cells become a lot like embryonic stem cells with that high level of potency.
So we can basically create patient-specific stem cells.
Exactly.
That's amazing. And without the ethical issues.
Right. The potential for personalized therapies with these cells is huge. And, Bailey and Loves, they even mentioned this interesting debate going on in the field.
Oh, what's that?
It's about the name for a specific type of stem cell,
Okay.
mesenchymal stem cell versus mesenchymal stromal cell.
Huh, interesting. What's the difference?
It's a bit nuanced, but it kind of boils down to our understanding of how these cells work.
Okay.
Some scientists think stromal cell is a better term because it emphasizes their role in supporting the surrounding tissue rather than directly becoming new tissue.
So it's more about their function.
Right. It's a reminder that we're still learning and refining our knowledge in this field,
For sure. So we have these incredible cells, but how are they actually used in, treatments right now?
Okay, so one of the most successful applications is in skin regeneration.
Okay.
Like, we can grow sheets of skin cells in the lab to treat severe burns.
Wow.
It's amazing, right?
It is, yeah.
And this is actually built upon the work of Rheinwald and Green, who they figured out how to culture keratinocytes. Those are the main cells in our skin.
Essentially, we're creating like a second skin for these patients.
Yeah, pretty much.
That's incredible.
It's not perfect yet, but it's getting better all the time.
Right.
And the potential for treating burns, wounds, even chronic skin conditions.
Huge, yeah.
Huge.
And Bailey and Loves also talks about articular cartilage regeneration,
Yeah.
which is very relevant for surgery.
Oh, absolutely, yeah.
What's being done there?
Okay, so articular cartilage, that's the smooth tissue at the ends of our bones in our joints.
Okay, yeah.
And it's really hard to repair.
I see.
But tissue engineering is giving us some hope. There's this technique called microfracture.
Microfracture.
Yeah, so they drill tiny holes in the bone, like underneath the damaged cartilage.
You drill into the bone.
It sounds intense, right?
Yeah.
But it releases stem cells from the bone marrow,
Okay.
and then those cells can help form new cartilage.
And is that effective?
It can be, yeah, especially for smaller defects.
Okay.
And even though the new cartilage isn't as strong as the original, it's way better than nothing.
That's true.
And it helps with pain and improves joint function.
Makes sense. And Bailey and Loves also mentions this other technique called autologous chondrocyte implantation.
Yeah.
What's that about?
So in this one, they take a small sample of the patient's own healthy cartilage cells.
Okay.
They grow more of them in the lab and then implant them back into the damaged area.
So it's like a personalized cartilage transplant.
Basically, yeah. It's more complex than microfracture, but it can be more effective, especially for larger defects.
I see.
And actually, organizations like the UK's NICE, they recommend this procedure for certain knee cartilage injuries.
Wow. So it's really moving from, research into actual practice.
It is. It's really exciting.
It is, yeah.
And that's just, with cells.
Okay, yeah.
But to make functional tissues and organs, we need more than just cells.
Right.
And that's where materials come in. They're the scaffolding for the cells to grow on.
Materials. Like, we're literally building structures for cells to live in.
Exactly. Think of it like building a house. You need that framework, right?
I get it. Okay, so what kind of materials are we talking about?
Well, there's a huge variety. We have natural materials like collagen and fibrin, which are already in our bodies.
So using the body's own stuff.
Yeah. And then synthetic materials like polymers and ceramics. And we can design those with specific properties.
To do what?
To guide tissue regeneration.
That's amazing. Can you give me some examples, like specific materials and how they're used?
Okay, so let's start with synthetic polymers.
Okay.
Like PLA and PGA. You might be surprised to know these are already used in the body.
That's what?
Sutures.
Really? Sutures?
Yep. And scientists have figured out how to make them into these intricate scaffolds, different shapes, sizes, depending on the tissue.
Wow. Actually, Bailey and Loves has this picture of a PLA scaffold, and it looks porous, like a sponge, but you can see the individual pores.
It's amazing, right?
It is, yeah.
And they can actually control the size of the pores.
They can?
Yeah, which influences how the cells grow and organize within the scaffold.
That's incredible. What other materials are there?
Okay, so moving on to bioceramics.
Bioceramic?
Those are really interesting for bone regeneration.
Okay.
So one of the most well-known ones is bioglass.
Bioglass.
Yeah, it's a special type of glass that encourages bone growth.
Wait, glass in the body.
I know, it sounds strange, but...
How does that work?
So bioglass has certain ions like calcium, silicate, and phosphate.
Okay.
And as it degrades, those are released.
I see.
And they stimulate bone cells to grow and attach to the bioglass.
So it integrates with the bone.
Exactly.
Wow. Does this mean, like, there's glass in my toothpaste?
You might be right.
Really?
Bioglass is used in some toothpaste, like Novamin, to help remineralize teeth.
Wow, that's fascinating.
It is.
Okay, what else? What other materials?
All right, next up, hydrogels.
Hydrogels, okay.
These are really versatile, and they have this unique property. They're hydrophilic.
Meaning?
They love water. They can absorb and hold tons of it.
Okay.
So they form these gel-like structures that can encapsulate cells.
Providing what?
Protection and nutrients.
I see. Are there, like, any real-world examples of hydrogels in action?
Oh, yeah, for sure. Remember the pancreatic islets we talked about?
For diabetes?
Yeah. So one challenge is protecting them from the body's immune system.
Right, yeah.
And encapsulating them in a hydrogel made from alginate, which comes from seaweed.
Seaweed.
Yep, it can protect.
So it's like a little shield around the cells.
Exactly. And here's where it gets really cool. we can combine hydrogels with 3D printing.
3D printing organs.
Yeah.
That's wild.
It's pretty amazing, right?
It is.
So they can use 3D printing to make super complex structures, layer by layer. Bailey and Loves even talks about these two techniques, fresh and slam.
Fresh and slam.
Yeah, they're really pushing the boundaries here.
Can you explain those?
Okay, so imagine you're building something delicate out of jelly.
All right. It would need support, right?
So fresh. It stands for free-form reversible embedding of suspended hydrogels, and it basically acts like a temporary mold. It supports the hydrogel while it's being printed.
Oh, so it was like a scaffold for the scaffold.
Exactly. And then SLAM, suspended layer additive manufacturing, it takes it a step further.
How so?
It uses a special matrix, a supportive one, that allows for higher resolution printing.
Some more detail.
Yeah, and it's easier to remove after the structure is done.
Wow. What kind of structures are we talking about?
Oh, everything. Cartilage, bone, blood vessels, even complex organs like the heart and liver.
Wow, that's incredible.
It is, right? Bailey and Loves even has a picture of a 3D printed carotid artery.
I have to see that.
It's amazing.
So 3D printing is really opening up all these new possibilities.
Oh, yeah, for sure. The technologies are still being refined, but they have huge potential.
Absolutely. But cells and materials, those are just part of the story, right?
Yeah.
There must be other things that influence how tissues regenerate.
Yeah, you're right. The final piece is molecules. Yeah. They act like messengers and guide the healing process. They can control inflammation, stimulate blood vessel growth, even reduce scarring.
Wow. So molecules are like the conductors of the regeneration orchestra,
That's a great way to put it.
making sure everything happens in the right order.
Exactly. And scientists are getting really good at using specific molecules to improve healing after injury or surgery.
That's amazing. Can you give me some examples of how molecules are being used, like real-world stuff?
Okay, so one cool example is in scar prevention.
Scar prevention.
Yeah. You know that whole cascade of events that happens when you get a cut?
Yep.
So there's this molecule, TGF-1.
TGF-1, okay.
It plays a big role in how much scarring you get.
So if we control that, we can reduce scarring.
Exactly. Scientists are working on ways to do that, like using molecules that block it.
Interesting.
It's a complex process, but it could be really beneficial for patients, especially burn victims.
Oh, yeah. That makes sense. Any other examples?
Another one is in treating ocular fibrosis,
Which is...
scarring in the eye.
Oh, okay.
So this can happen after an injury or infection, and it can lead to vision loss.
Wow.
But researchers have found this molecule, decorin, that can help prevent that scarring.
How does it work?
Well, it binds to collagen, which is the main part of scar tissue.
Okay.
And by binding to it, it helps regulate its formation.
So less scarring.
Exactly. And the cool thing is, they're delivering it through eye drops.
Eye drops. That's so simple.
It is, and it's really effective. Bailey and Loves even shows how well it works.
So we're not just growing new tissues, we're also getting better at controlling how they heal.
Right.
This is all so incredible.
It is. It's an exciting time. We've covered a lot, from cells and materials to molecules and 3D printing, and we're only just scratching the surface.
You know, it's amazing. But I'm also realizing there must be challenges and risks, too, with all this, right?
Of course, safety is always the top priority. And while the potential is huge, there are definitely hurdles we need to overcome.
Like what? What kind of hurdles?
Well, one of the biggest concerns is tumor formation.
So these therapies could cause cancer.
It's a possibility, but scientists are very aware of this risk and are working to minimize it.
That's good to hear.
Yeah, it depends on the type of cell, how it's manipulated, where it's implanted, all that.
Makes sense. What about infection? Like transmitting infections?
That's another concern, especially with donor cells.
Yeah.
There's always a chance, however small, that something could be transmitted. So strict screening and manufacturing guidelines are super important.
I can imagine. So it's not as simple as just growing new tissues. There's a lot to consider.
You're right, there is. But, you know, amidst the challenges, scientists are always working to improve safety. Like, Bailey and Loves mentions this thing called transdifferentiation.
Transdifferentiation.
Yeah, it's where one adult cell type is directly reprogrammed into another without having to go through the stem cell stage.
Oh, interesting. So that could, like, bypass the tumor risk.
Potentially, yes. It's
Yeah.
still early, but it's promising. And of course, when we use a patient's own cells, there's no risk of rejection.
Which is a huge plus.
Absolutely.
Okay. So with all this in mind, what does the future hold for all of this? What should surgeons be like looking out for in the next few years?
Oh, the future's really exciting. Bailey and Loves highlights some cutting-edge stuff.
Like what?
One area is using extracellular vesicles for signaling.
Extracellular vesicle.
Yeah, so these are tiny packages released by cells, and they contain all sorts of molecules.
Okay.
And they can influence cell behavior and promote tissue repair.
So they're like targeted delivery systems.
Exactly, a more precise and less invasive approach.
Very cool.
And then there's CRISPR-Cas9.
Ah, CRISPR, yeah.
That's a real game changer. It lets scientists make really precise changes to DNA sequences.
So what does that mean for tissue engineering?
Well, we could correct genetic defects that might be preventing regeneration or even enhance the function of engineered tissues.
Wow. So we could make tissues that are more resilient.
Exactly, and even make cells more compatible for transplantation.
It sounds like a whole new era of medicine.
It really does. And personalized medicine will be huge in all this.
How so?
By analyzing a patient's genes and their specific disease, we can tailor treatments.
So really personalized regeneration.
Exactly.
Wow. But with all this power comes responsibility, right?
Absolutely. Bailey and Love stresses the need for new regulations to keep up with all this.
To make sure it's safe.
Yeah, and effective.
Yeah.
And then there's point-of-care manufacturing.
What's that?
So if we're going to make truly personalized therapies, we need to be able to manufacture them quickly, maybe even right at the bedside.
Mini factories and hospitals. Wow.
It sounds crazy, but it's getting closer. This field is moving fast.
It is. This has been incredible so far. I'm kind of blown away by all this.
It's pretty amazing stuff.
It is. And I feel like we've only scratched the surface.
We have, but hopefully this gives you a good foundation, you know?
Yeah, it definitely does.
It's a field that will shape the future of medicine and surgery. Keep an eye on it, and it really makes you think, you know? Like, if we can actually regenerate tissues, even grow organs in a lab.
Yeah.
I mean, what does that mean for the future of, well, everything? Healthcare, what it means to be human?
Big questions, yeah.
Big questions.
But before we get too philosophical, I do have a more practical question.
Sure.
You mentioned earlier that scientists are always trying to improve the safety of these therapies.
Right.
What are some of the specific concerns there, and how are they being addressed?
Yeah, good question. So one of the main concerns with any kind of transplant is rejection.
Right, the body rejecting the new tissue.
Exactly. If the immune system sees the new cells as foreign, it'll attack them.
And then the treatment fails.
Exactly.
So how do we get around that with tissue engineering?
Well, there are a few things we can try. One is immunosuppressant drugs.
Like they use in organ transplants.
Exactly. But those have a lot of side effects.
Yeah, and risk of infection.
Right, so we'd rather not use them if we can avoid it.
For sure. Any other options?
A really promising one is using the patient's own cells.
Oh, okay.
That's called autologous transplantation.
Autologous.
And basically, there's no risk of rejection because the body recognizes the cells as its own.
That makes sense.
Uh-huh.
Are there any downsides to that?
Well, getting those cells and growing enough of them can be tricky.
Okay.
It takes time, it can be expensive,
Yeah.
and sometimes it's just not possible for certain tissues.
I see. But it sounds like a really good option when it works.
It is.
Okay, so that's rejection. What about other safety concerns? Like contamination during the manufacturing process?
Yeah, that's a big one. We have to make sure these cell products are absolutely sterile.
Of course.
So they're produced in special facilities, clean rooms, with super strict controls.
To prevent any bacteria or anything getting in?
Exactly. And there's rigorous testing throughout the whole process.
To make sure it's all good. And what about long-term safety? Do we know if these engineered tissues will, like, keep working properly over time?
That's something we're still studying.
Yeah.
We need to follow patients long-term to see how they do.
To make sure there are no, like, unexpected problems down the line.
Exactly. There's always that possibility, so ongoing research and monitoring are key.
Makes sense.
It's,
Sounds like there's a lot to consider.
There is. It's a new field, but we're learning more all the time.
Okay, so we've talked about safety, but what about cost? I mean, all this sounds super complex and high-tech.
Right.
Will these therapies be available to everyone or just, people who can afford it?
That's a really important question.
It is, yeah.
And right now, a lot of these therapies are very expensive.
Yeah, I can imagine.
But as technology gets better and we figure out how to produce things more efficiently,
Okay,
the hope is that the costs will come down.
that'd be great.
Yeah. And there's a lot of research focused on making things more affordable.
It would be a shame if these treatments were only available to, a select few.
Absolutely. Everyone should have the chance to benefit.
For sure. Okay, so shifting gears a bit, you talked earlier about some really cutting-edge stuff.
Yeah.
extracellular vesicles and CRISPR-Cas9.
Right.
Those sound almost like science fiction.
They do a bit, yeah.
Can you explain a little more about how they're being used?
Sure. So extracellular vesicles, EVs for short,
Okay.
they're like tiny packages that cells release.
Okay.
And they're filled with molecules, proteins, lipids, even genetic material.
Interesting.
They act as messengers between cells.
I see.
And they can affect things like growth, cell differentiation, even the immune response.
So are scientists using these EVs to, deliver treatments to specific cells?
Exactly.
Like targeted therapy?
Yeah, you can think of them as natural delivery vehicles.
Wow. And we can engineer them to carry specific things?
You can. It's a much more precise way to deliver treatments.
That's amazing. What about CRISPR-Cas9? How does that fit into tissue engineering?
CRISPR is a huge deal for all of medicine, really.
Yeah.
But for tissue engineering, it means we can edit DNA with incredible precision.
And that allows us to do what?
Well, we could potentially correct genetic defects that prevent regeneration.
Okay.
Or even make engineered tissues function better.
So stronger, healthier tissues.
Exactly. And we could modify cells to make them more compatible for transplantation.
To reduce the risk of rejection.
Right.
This is incredible. It really does feel like a whole new era.
It does.
But are there ethical concerns with, editing genes like this?
Oh, absolutely.
Hmm.
Anytime we're talking about manipulating our DNA, we have to be extremely careful.
Of course.
There's a lot of debate about how far we should go.
It's a big question, yeah.
It is?
Okay, so one last thing before we wrap up.
Sure.
What about regulation? How are agencies keeping up with all this, making sure it's all safe and effective?
Yeah, so agencies like the FDA in the US and the EMA in Europe. Okay.
They play a huge role in this. They have strict guidelines and standards for any new medical product.
Including these engineered tissues.
Absolutely.
Yeah.
They have to prove that these products are safe and that they work before they can be used on patients.
So they're like the gatekeepers, making sure everything is done right.
Exactly.
Mm.
And it's a constantly evolving process. New technologies are always emerging.
Right.
So they have to adapt and update their guidelines to keep up.
While still making sure patients are safe.
That's the priority. It's a balance.
It is. But it's good to know that these systems are in place.
Absolutely. It takes collaboration between scientists, doctors, regulators, and the public.
To make sure we're doing this right.
Exactly.
This has been an amazing discussion. I feel like I've learned so much.
It's been a pleasure.
Really, I'm blown away by the potential of all of this.
It's incredible.
It is. And I feel like we've only just, scratched the surface.
We have.
Yeah.
But hopefully this has given you a good overview.
It has, definitely. It's a field that will shape the future of surgery. It's important to stay informed.
I agree, 100%. Okay, so before we move on, let's take a minute to recap what we've covered.
Sure.
Just to make sure we're all on the same page.
Good idea.
So we started with the basics, right? Cells, materials, and molecules.
Right, the building blocks.
And we talked about stem cells, how amazing they are.
Their ability to self-renew and differentiate.
Yeah. And the different types, somatic, embryonic, iPSCs.
Exactly. And then we moved on to biomaterials, the scaffolds.
Natural and synthetic.
Right. Collagen, fibrin, polymers, ceramics, all those.
And how they provide that structure for cells to grow.
Exactly.
And then we can't forget molecules, the conductors.
Yeah, the messengers that guide the healing process.
Yeah, controlling inflammation, blood vessel growth, scarring.
And we talked about some specific examples of how they're being used, like TGF-1 inhibitors for scars.
And the Decorin eye drops.
Right. Amazing stuff.
It is. And then we got into the more advanced stuff, 3D bioprinting.
Fresh and slam.
Yeah, those techniques.
Yeah.
And how they're being used to create really complex structures.
It's mind-blowing, really.
It is. And then we talked about the challenges too. Rejection, contamination, long-term effects.
But also the safeguards that are in place to address those challenges.
Right. Like the testing and the manufacturing standard.
Exactly. And new approaches like using the patient's own cells.
And then we touched on the bigger picture. Access, affordability, ethics.
Important considerations.
Very important.
This field raises a lot of questions.
It does. Okay, so that was a good recap, I think.
It was.
It helped me solidify some things. But we've only scratched the surface here.
We have. This field is vast.
It is. So any final thoughts you want to leave our listeners with?
Well, I think the main takeaway is that this is a paradigm shift in healthcare. We're not just managing symptoms anymore.
We're actually repairing and regenerating.
Exactly. And it's happening at an incredible pace.
I know. What seems impossible today could be commonplace tomorrow.
Right. So as surgeons, we need to stay on top of this, keep learning and embracing the possibilities.
I totally agree. This is really inspiring stuff.
It is. It's an exciting time to be in medicine.
It is. Okay, one last question, just for fun.
Okay.
What do you think, where will all this lead? What's the ultimate future of tissue engineering?
Well, who knows, right? But maybe one day we'll be talking about all this over a cup of coffee,
Yeah.
grown from lab engineer to coffee beans.
Now that's a future I can get behind. Thanks for that image and for this amazing discussion.
It was my pleasure.
I feel like I have a whole new perspective now.
That's great to hear.
It is. And for our listeners, keep learning, keep asking questions, and, keep pushing the boundaries. This field is full of potential.
It is.
Yeah, it's amazing to think how far we've come. Like from basic skin grafts to, 3D printing organs and editing genes.
It is pretty remarkable.
And it sounds like there's so much happening, new discoveries all the time.
Oh, yeah, there's a ton of momentum, like tons of new stuff coming out all the time.
What's driving all this progress?
I think it's a few things coming together,
Yeah.
like advances in stem cell research, material science, bioengineering.
Yeah.
And we're also just understanding more about how tissues develop and repair at like a molecular level.
So it all these different pieces fitting together.
Exactly.
With all this excitement, we can't forget about the challenges, right?
For sure.
And the ethical stuff, too.
Yeah, we have to be careful and responsible with all this new power.
Absolutely. What do you see as, the biggest challenges going forward?
Well, one of the big ones is making sure these therapies are accessible to everyone.
Affordability.
Yeah, exactly. We don't want a system where only the wealthy can benefit from these treatments.
Right. Everyone should have access.
Exactly. It's a social justice issue.
Absolutely.
And it's going to take a lot of effort to solve it. More research, better regulations, new ways of delivering healthcare that focus on, making these things affordable.
It's a big challenge,
It is.
but we have to address it.
I agree. Okay, so before we wrap up, I want to touch on something you mentioned earlier
Okay.
about this field challenging our understanding of what it means to be human.
Right.
Can you talk more about that?
Yeah, I think one of the really profound things about all of this is that it's blurring the lines between natural and artificial.
Okay.
We're basically creating living tissues and organs in a lab, like mimicking nature.
Yeah.
And that makes us question, our relationship with our bodies.
Yeah.
What does it even mean to be alive if we can create and replace parts of ourselves?
That's a deep question.
It is. And it's one that philosophers and ethicists are really grappling with.
I bet it's something we need to think about as a society.
Absolutely. As this technology gets even more powerful, we have to consider the implications.
For our values, our beliefs, everything. Exactly. It's not just about science. It's about what it means to be human.
That's a great point. Science and technology, they don't just change what we can do. They change how we see ourselves.
Exactly.
Wow. Well, this has been an incredible deep dive. I feel like I've learned so much, and honestly, I have even more questions now.
That's good. It means you're thinking critically about all of this.
It's a lot to take in, that's for sure.
It is. But it's exciting stuff.
It is. I'm really glad we had this conversation.
Me too. It's been a pleasure.
Thank you so much for joining us on this journey into tissue engineering and regenerative medicine. We hope you found it as fascinating as we did. And for all of you listening, keep learning, keep asking questions, and, keep pushing those boundaries. This field is full of possibility.
Absolutely. The future is bright.